This video is intended to support your learning for the respiratory clinical integrative puzzle and hopefully will serve as a review and to prop up your understanding of assessment of oxygenation and ventilation using blood gas analysis. So just a quick review of CO2 and O2 in terms of transport, production, and metabolism. This is a stylized cell, little mitochondria, where it all happens and energy is produced using oxygen that has come from the animal ventilating, bringing oxygen into the alveolus, diffusing across into the capillary blood, out into the arterial blood supply, and to the cell for energy production. The byproduct of energy production, of course, is CO2, which comes back into the venous blood to be diffused into the alveolus and ventilated away. So in the end, you have a venous side that has high CO2 and low O2, and an arterial side that has high O2 and low CO2. So this is an example of a blood gas. So this is an arterial sample of blood that's been put into a machine called a blood gas analyzer. Depending upon the fanciness and the cost, generally, of the machine, you'll get more or less values, but all blood gas analyzers will give you both blood gas information, by definition, of course, but they'll also give you acid-base because CO2, which is a part of the blood gas analysis, is of course very tied up in acid-base regulation. Before we get into specific examples, kind of a couple of golden rules. One is that you should always view oxygenation, or PaO2, in light of ventilation and FiO2. So that means you have to view oxygenation in light of how hard the animal is breathing or ventilating to get to that level of oxygenation, and also how much you are supporting it or not with supplemental oxygen administration to get to that level of oxygenation. Generally speaking, the PaO2 should be about 4 to 5 times the FiO2. And here are normal values for PaO2, about 85 to 100. PaCO2, a bit more species specific, but for the dog, about 34 to 42. So remember we said that the PaO2 should be about 4 to 5 times the FiO2, or the fraction of inspired oxygen. And we can use this known relationship to our advantage when we're comparing animals who are breathing differing amounts of oxygen. So it's just math, and by convention the FiO2 is expressed as a decimal point, so instead of saying 21%, we're going to say 0.21. And so here are a couple of examples. If you have an animal whose PaO2 is 100 millimeters mercury, who's breathing 21% oxygen, its PaO2 to FiO2 ratio is 476, which is normal. If you have an animal whose PaO2 is 100, but who's breathing more oxygen to get to that 100, that's going to be worse lung function. PF ratio is 250. So in sum, the PF ratio can be used to evaluate the severity of gas exchange abnormality when an animal is breathing supplemental oxygen. So we'll use these two cases to demonstrate the concept that the PF ratio can be used to assess oxygenation in animals who are receiving supplemental oxygen. So just looking at the blood gas, this dog on the left is mildly hypoxic with a PaO2 of 77. Remember, normal is about 85 to 100. And this animal is not. His PaO2 is 185. Ventilation in the two animals are held constant for the sake of explanation here. And the thing that differs is that the FiO2 is 21% in one of them and 100% in the other. So how do we decide whose lungs are worse? We're going to do a PF ratio, and so we're going to say 77.1 divided by 0.21 is about 367, whereas we don't even really need to do the math here. This is 185 on the Airedale divided by 1.0, that's 185. So remember, normal PF ratio should be 4 to 500, so clearly the Airedale has a more serious gas exchange abnormality than the Westie does. We'll use these same two dogs again, but with slightly different blood gases to explain the importance of evaluating ventilation in light of a given oxygenation. So we're going to hold FiO2 constant, so they're both breathing room air. And in this one, the PaO2 is 64.5 as it is here, but this dog is working a bit harder and hyperventilating more to get to that same kind of marginal PaO2, whereas this dog is hyperventilating, just not as much. And finally, in this last example, we'll look at the effects of hypoventilation on PaO2. So the first thing to know is that for every 1 millimeter rise in PaCO2, there's typically a 1 millimeter drop in PaO2 if it's just due to hypoventilation alone. And so let's look at these two blood gases. The first is a dog who is breathing like this. So this dog has a marked inspiratory dyspnea. That sound that you're hearing is called stridor. And this is the blood gas. The PaO2 is 61.9, so markedly decreased, and the PaCO2 is 62, so increased. So this dog is by definition hypoventilating because the PaCO2 is above the normal range. And if you look at the difference between how much the CO2 has risen versus how much the O2 has fallen, it's about a 1-for-1. So 62 is about 22 millimeters of mercury above the middle of the normal CO2 range, about 40. So 62 minus 40 is about 22, so it's 22 above normal, whereas the PaO2 is about that much below normal. So probably this dog's hypoxemia can be explained entirely by hypoventilation. In contrast, let's look at the other blood gas. For the sake of argument, we're holding PCO2 constant, and we're also, by the way, holding FiO2 constant. And this PaO2 is quite a bit lower. Let's look at how this dog is breathing. Now, you've seen this video before in one of your lectures in the respiratory block, and that's called, this dog was hit by a car. That's called a flail chest, where a segment of chest wall and ribs are fractured in multiple places. And on inspiration, the flail segment goes in and creates a pleural space defect and causes hypoventilation. And also the pain of having rib fractures causes hypoventilation. But why is the PaO2 even more decreased than can be explained by hypoventilation alone? We'd have to suspect that there's also a problem with the pulmonary parenchyma, and that there's an issue at the level of the alveolus with gas exchange. And the most likely explanation is that this dog also has pulmonary contusions. And for completeness sake, the bulldog in the previous slide might have had an airway something like this upon laryngeal examination and would need to have his airway bypassed, whereas the dog who'd been hit by a car would likely need to undergo general anesthesia, positive pressure ventilation, and stabilization of that flail segment. So I'll leave you with some key points. I hope you've enjoyed this little video, and feel free to contact me if you have further questions. Thanks.